So today we will do some practical exercise, specifically exercise number 7 to calculate the course project task related to spectrum. So what we want to do is to calculate and display modulated signal spectrums for specific parameters which are individual, and we want to have two pictures: magnitude spectrum for periodical sequence of ones zeros and spectral power density for random sequence of ones and zeros. So that is magnitude spectrum and energy spectrum, which we covered in the lecture just now. So we will use the same formulas to specify them. Now, for your individual parameters today, we are going to need just few of them, mainly the carrier frequency, the modulation type, and if you have frequency shift keying BFSK, you are going to need to have index also. Yes, so for everybody who is having it 0, it's not there. I will replace it later to these asterisks, yes, to make it more specifically clear that you don't need this parameter, but you need to have this as a number, like 3, 2, or 4, yes, depending on the parameter values. So for me, it's 4, yes. Now, carrier is 2, and the modulation types, I will display all 3 of them for you, so that you need only to do only one as per your parameters. So let's start with entering all our parameters we are going to need. So this is the course project task 7, calculating spectrums. Yes, so calculation of BASK, BFSK, and BPSK spectrums. First things first, initial parameters that are going to be also, by the way, no, we also need one more parameter actually. Apologize. We also need to know symbol duration, because that is affecting the spectrum bandwidth. Yes, so how wide is your spectrum in megahertz or gigahertz wise? So that is also an important parameter. So for me, symbol duration is 60 nanoseconds, which I'm going to input. The symbol is 60 e minus 6, 9, sorry, nano is minus 9. So that is symbol duration, seconds. Next is carrier frequency, which I will denote as F0. So that is 2.0 gigahertz for me. 2.0 e plus 9. That is carrier frequency, hertz. And also I need to know modulation index if you have BFSK. So I do have MF. That was 4.0 for me. 4.0 BFSK only modulation index. So let us then begin with working on amplitude shift keying, because it's going to be base for everybody anyway. So we are going to need to have this as a function. So we are going to create a let me just save it. Let's say spectrum 2025, like that. So first we need to we specify a formula to calculate BASK periodic signal spectrum. So that is available both in lecture slides and also in this document. if we scroll further, you will see some formulas. So we will need to use the formula for this CBASK calculation. Now, it would be a nice idea to actually implement this as a function, because if you have BASK, well, you simply call that function. If you have BFSK, you are going to need to call this function for two different frequencies, omega 1 and omega zeros twice, and for phase shift keying, you also need to call it, well, preferably twice, probably, yes? So basically, it would make sense to actually implement this in some kind of a function. Now we can use for this purpose separate file, but that would be overkill. Yes, so it's better to specify a function inside of your code. But again, there are some issues, like in MATLAB, for example, it might not necessarily work just the same way as in Octave, so it depends whether you need to have it at the beginning or at the end of the file. So our approach will be to use something called as anonymous function. So let's check out fast MATLAB help anonymous function. So the idea here is that these functions are, oh, sorry, not necessarily having its separate file, but they still have some name. Yes. So let's see some example. Uh, let's say, well, they use some funny names. Okay, so let's say this one, for example. So they create a function to calculate the square root, or not square root, but square of the signal this way. So you give a function name, let's say sqr. In our case, it's going to be BASK, then equal, then this add symbol with the parameters you are going to specify externally to your function, then you calculate the value. So, for example, let's make it a very simple demonstration, like let's say I want to have to convert my frequency of 0 into a radian per second, that is cyclic frequency omega 0. Yes, so let's say omega is going to be a function which I can run, which inputs specific parameter, let's say some x. That's the name of this parameter, internal name. It doesn't necessarily have to be any one of these. And then you write whatever actions you want to make with this parameter. So in our case, we want to multiply it with 2 and with p. So doing so, I have created a new function which is called omega, for which I can now run anything I want to. So for example, now I'm going to say omega of f0. So this is going to calculate double p of f0 and print it to console. So here you can see this number, and if I have f0 multiplied by 2 by p, it's actually the very same number. So that's how we have created function which I can now call multiple times, here, later, and so on, by simply specifying some parameter. Now let's see if I can say, for example, okay, so if I say can specify some numbers, and one of these numbers are going to be taken from these, for example, mf plus x. So now if I specify, let's say number 5 here, what's going to happen is it knows mf. Yes, I don't have to specify it here like so, yes, so that it knows. It actually can get it from the global variables, yes. So that means I only need to specify whatever inputs I care to use. In my particular case of the formula of the spectrum, will be only one variable parameter, which is going to be k in this particular case. Or maybe let's better use k omega, because this way it will be convenient to use that later for this omega. So k omega, or simply omega, yes, is going to be literally the only variable parameter here, because omega 0 is going to be fixed, tau is specified is fixed, j is fixed, u is fixed, everything is fixed except for this omega parameter that we want to calculate the spectrum for. So in our case then, we are going to have a function to calculate BASK over the parameter w, which is going to be uh, frequency, yes, so angular frequency specifically. And here we will write down this entire formula of the spectrum, which is j u divided by 4, which let's assume for simplicity, yes, for simplicity, assume that u is just 1, yes, to, kind of not to haggle it around, just to get rid of it. So u versus 4, sorry, also multiply it with 1i, that is complex unit, yes, imaginary unit, multiplied with, now we have to calculate this sin of x versus x. Yes, that's actual expression. Now here we have to be really careful, because the straightforward and easy approach would be to type accordingly sin of a versus a. Well, let's try that. Sin of omega, element-wise, divided by omega. So our omega is going to be the set of frequencies. We are going to calculate all of them with one call of this function. So that is an array. And because of that, we have to divide array element-wise. First with first, second with second, and so forth. Now, let's say I want to calculate BASK of 0. Now, that is going to produce some problem for us, not because you try to divide by 0, but even more complicated one. Now it's going to say it's not a number, and also giving a warning divided by 0 in anonymous function. What does it mean not a number? Well, if you had calculus, higher mathematics course, then you should know that there exists such remarkable limit when x is approaching to 0 of sin x versus x, which should be equal actually to 1. Yes, that is because when x is very small, sin x and x are essentially the same. Yes, well, you know how sin wave starts like this and goes so. So at the very, very small levels here, that goes exactly same way as the straight line, which would be like so. Yes, so we are speaking about very small values. So essentially now if you put 0 versus 0, computers tries to calculate this and gets not a number. Yes, so it cannot do that. It's not even infinity, because in MATLAB, if you say you calculate 10 versus 0, then it's going to say it's infinity. Yes, well, kind of approaching infinity as a limit, say. Yes, but if you kind try to calculate uncertainty, it cannot do so. Yes, because of that, there actually is a function called sync, which now works properly. Now, so sync calculates sin of x versus x, although not exactly, it's more like sin of px versus px. Internally, by processing via, let's say, if condition, this specific case. So if x is 0, then return 1. As simple as that. If not, else, then we can calculate actually sin of px versus px. But for us, it's inconvenient because we already have p in our omega, so we are going to have it again. Because of that, we are going to have to calculate sin of omega versus p to compensate for the fact that it is going to multiply with p anyway when it calculates, so it's going to cancel out and we will calculate for real omega. Yes? So with that in mind, we are now going to actually replace this sin with a sin omega divided by p. And this doesn't need is needed here, not no longer needed here, yes. But that's not actually all of it, or that what we wanted to calculate, because in formula it's not just omega. Yes, it's omega minus omega 0 multiplied by tau versus 2. So then we need to now say that this is omega minus omega 0 multiplied by ts, symbol duration, by half, and then divided by p, so all of this bracket. Now, however, it's going to say I don't know what is omega 0, so let's calculate that. Let's find angular carrier frequency, radian per second. So that's quite simple to do. It's just f0 multiplied by double p. Now our function actually knows anything it needs to know and is calculating a complex spectrum. See, I have specified 0 and it calculated some 0 real part and some not exactly 0 imaginary part. Now, if you look closely to this formula, you will notice that actually that's in line with what we have specified. We have specified that our spectrum is completely imaginary. It has no real part. It has only imaginary part with this J part, yes? And that is it. So no surprise that it found that real part is exactly 0, whereas imaginary part has some very small value, which is almost 0. And this is a complex number. It's what I was saying about. Yes, you see this as a complex number, and you can work with that as you want. So now we have this function specified to calculate the amplitude spectrum of periodical signal. Yes, so now we can use that to calculate it for our specific set of frequencies. However, before that, we still need to decide one thing. What is your range of k for which you need to calculate? Because, well, here it's given for granted that there is some number k, yes, that is integer number, but we don't necessarily want to see all of them. We want to see where is our spectrum. Well, of course, we could have, let's start with a straightforward approach and then say, so I'm going to put that in some lines like so to denote that this is our actually main function that's going to be used mostly. Yes. And here now I am going to say we specify a range of k, like from 0 all the way up to 200, for example. And let's hope that it will be enough to see some spectrum, because it might not be, I don't know, yes, as of now. So we need to calculate omega, that is base, this omega capital base function, which is calculated as p divided by tau. Yes, so we can easily do so. Omega base, that will be p divided by symbol duration. Then we specify range k from 0 to 200. That is starting point, ending point. Since this is an integer number, it has to go with a step of 1, which is automatic. Yes, step of 1 is automatic. And we don't need to change that. Then we can calculate spectrum component Ck as BASK of k multiplied by omega base. So if we run it, I put the semicolon so it doesn't print anything. So we see some numbers which we can then stem. Wait, it's a complex number, so to stem it I need to have absolute value. And well, we can see that the spectrum is still increasing and very, very slowly. So 200 is not really an option. Well, maybe 1000 is going to look better, but again, we are guessing. But there is actually a way to know for certain where exactly our spectrum is supposed to be. So I took deliberately much more than necessary to show you that here, that is our spectrum, yes, and our spectrum is centered at the value, well, something around like 242 or 3 or something like that, yes. So it would be a good idea to actually start from this point and take, let's say, 10 samples in one direction, 10 samples in another direction to see the most important part of the spectrum, which is difficult now to zoom because it's a lot of points, it's also a little bit lagging. So to see our spectrum like so, for example, yes. Now let's do that stuff. Uh, for that, we need to know what is this number of this central harmonic of this carrier representing frequency omega 0. And that is has to be some k0 multiplied by omega capital. Yes, now from this expression we can easily express k0 as omega 0 versus omega capital. And that's it. Yes, we have omega 0 calculated, we have omega base calculated, so we now can express k0. So let's find out precisely what is this number. And accordingly, I'm going to erase that part. So let's find k0 value for omega 0 carrier frequency. That's actually where frequency is a single one, where your spectrum will be located around center of your spectrum, yes? Essentially, center of spectrum. So k0 is, as I say, omega 0 versus omega base. Let me actually print it out to see what's it equal to. So k0 is actually 240, yes? So uh, with that in mind, now I can say, let's specify a range of, okay, so this goes away because that range didn't work. K0 minus 10 all the way up to K0 plus 10. So 20 harmonics, including center, so 21, 10 in the right side, 10 in the left side, and 1 in center. So that should provide some good to see spectrum for us. That will be K equal to K0 minus 10 starting point, K0 plus 10 ending point. And calculate the spectrum, BASK spectrum. So that would be Ck equal to BASK of omega k uh, omega base. Well, actually, now kind of think of it, when we will need to change omega 0 to omega 1, we have no way of doing so. So it would be actually a good idea to specify here that it's this omega. Yes? Or we can say omega difference. Because other way around, we will not be able to say that this is omega 0 or omega 1. It's always going to take omega 0, but we will need to change that. So I'm going to say here that omega difference is omega 0, or k, omega minus omega 0. So this way, you can specify directly here, minus omega 0, or omega 1, or omega 2, whichever will be necessary for you. So that is a good idea. So whenever we calculate this equal to omega 0, we hit 0 in this difference, right? But because we use a sinc function, this is going to be properly processed all the way up to 1. Yes, and you multiply this 1 by 1 divided by 4. So the maximum of your amplitude spectrum should be 0.25. Yes, that is 1 divided by 4, because sync gives 1, and all the others numbers are ending up to be, well, 1 divided by 4. Yes. So now let's actually, while we are at it, plot this as well. Plot this spectrum as stem figure. That's going to be, let's just for now say stem of C, absolute value of ck, grid on, next label frequency harmonic, y label is magnitude. So that is amplitude spectrum. So if you run it, it works out, and then you have a picture of your spectrum centered around some funny numbers, yes, because we did not specify any frequency range on x-axis, but otherwise this picture is actually the same as it was in the lecture materials. Well, I can actually even open it for comparison. So we speak about this upper picture one. Yes, you also see that it's 0.25 maximum. It's a little bit compressed vertically because now there are two pictures, but we will add the second one also. So 0.25 maximums, just like so. And what if now, before taking next step to energy spectrum, um, so let's say this is calculate BASK spectrum, calculate magnitude spectrum. And now I want to calculate, let's say, not BASK, but BFSK or BPSK differently, yes? Now, it's still easy to do using the same function, the same range of variables. However, if you have frequency shift keying, yes, then, so let me specify BFSK only, then you need to calculate frequency f1 and frequency f2. And accordingly, well, we will might as well start with omega 1 and omega 2 so that we don't have to convert them. Yes, so basically, we need to calculate them. In order to do so, you need to know the index of modulation, which is provided for you, and the base frequency, which we have calculated. So the delta omega can be calculated as product between index and base frequency. So let's do that. Delta omega is going to be modulation index multiplied by omega base. Then omega 1 is going to be omega 0 minus delta omega by half, whereas omega 2 is going to be omega 0 plus delta omega by half. So now you have two of these frequencies for BFSK and can actually create a BFSK signal. Well, I don't need this. No, wait. No, I don't need this one. I already have it here. The same modulation for frequency omega 1 and omega 2. So say, well, actually I am going to have them separate. So calculate BASK spectrum, magnitude spectrum. And this one is calculate BFSK, magnitude spectrum. So now I am going to need to have CK1, that is BASK K omega base minus omega 1, CK2, which is BASK K omega base minus omega 2. Yes, so as per formula. Now this is for omega 1, this is for omega 2. And also I need to have these complex exponents as well. Yes, multiplied to the CK1, which is going to produce me the desired output. So CK, therefore, is going to be CK1 multiplied element-wise, because it's an array, with an exponent of JK omega capital tau divided by 2. So that's 1i multiplied by k multiplied by, sorry, omega base. Oh, wait, how was it? Yes, it was without underscore, omega base, multiplied by t symbol divided by 2, plus the same stuff for ck2, but it's with a minus argument, minus this thing, yes? And this is ck2. Now, it should produce the frequency shift keying spectrum instead. Or some error if I made some error. Yes, it doesn't know what is omega 1 because omega 1 is calculated after I have tried to calculate the spectrum. So I need to move this up front here. Yes, if we first calculate omega 1, then we say omega 1 here. Otherwise, it was not known. And the spectrum wise, you can now see the picture here. Yes, that is for frequency shift keying. Now, in my particular case, I'm missing some center value here. It just happened to be compensated, probably. Not sure exactly. But so far, it seems to be symmetric and correct. But also, let us actually specify some real frequency hertz here. It's not difficult at all, because what we need to do is to say that this is actually k multiplied by omega base divided by p divided by 2. So now these are going to be frequency in hertz. So if I run it, then you see that in the center here, I have a frequency of 2 gigahertz. which is one was given to me as a parameter. So in these practical exercise parameters, in my configuration, I had 2 gigahertz carrier frequency, yes, 2.0. For somebody of you, it's going to be 2.5, 1, 1.5, 2, 0.5, and so on. So that is the number you are expecting to see in the center here of your picture. Now let me make this spectrum a little bit thicker line to see it better. So I'm going to add parameter called line width. And also I am going to make these pictures occupy only half of this window because the next spectrum I'm going to display is going to be an energy spectrum. So I am going to use subplot, 2 rows, 1 column, picture number 1. So here we now have this frequency shift keying spectrum. If I want to display amplitude shift keying, I will just comment this line and you will see amplitude shift keying spectrum. If I want to display a phase shift spectrum, I need to calculate that also. Calculate BPSK magnitude spectrum. Essentially, this is exactly the same approach with one exception, that you are going to use omega 0 here, well actually 2 exceptions, and minus sign here. Yes, so basically we change omega 0, and we change it to sign. So now that is the phase shift keying. And if I run it, you will see the same picture as for amplitude shift keying, but with the central value missing. Now, because central value does not consume energy anymore, you can see that these other values actually even exceeded 0.25, well, 0.25, which was here, yes? So that energy went to other components which contain your information. And that is why actually this modulation type will in future will show as the most robust and noise resistant, yes? Because all of the energy is given to information. And even more so, we use absolutely opposite signals with opposite phases. Yes, so that's also good. So that gives you ability to calculate the spectrum. So if you calculate amplitude shift keying, you just use this function with a frequency omega 0. If you need to calculate the frequency shift keying, then you calculate two of these modulations, one with omega 1, one with omega 2, then multiply each with its corresponding shift parameter, and there you have it. For phase shift keying, you generate also two of them, but with the same frequency, essentially meaning that you kind of could put that outside of brackets, factor out, but to be consistent and show it how exactly it's similar to frequency shift keying, I decided to use the same approach. But don't forget to change the sign to minus though, because for phase shift keying, we find a difference of them. So that takes care of the part A of the task where you need to calculate the magnitude spectrum for 1, 0, 1, 0, 1, 0, 1, 0, and so on signal. Now for spectral power density as an energy spectrum as uninterrupted line, we need to change our approach a little bit. Not much, because, well, essentially, if we check the formula right, all that changes is that your otherwise discrete frequency k omega becomes a continuous value, making the full line, and you also multiply with double t. So basically that is it. Yes, we need slight modifications to this formula, so that's usable again to get an energy spectrum. So let us do that. That's going to be part 2 of this task, part 2, energy spectrum. So again, we'll start with amplitude shift keying, then frequency shift keying, and then phase shift keying. Well, for phase shift keying, it's actually very easy to go from amplitude shift keying. You just multiply with 2 and you are done it. But for amplitude or frequency shift keying, well, you will need to calculate two modulations as before. So BASK case, well, actually, regardless of the case, first we specify continuous frequency range. So with starting frequency of omega 0 minus k omega base, all the way up to omega 0 plus k. Wait, no. I mean, for k, no, it was k0 minus 10 all the way up to k0 plus 10, yes? But these were integer numbers. Now we are going to say with a step of 0.01. So we don't take integer numbers like 241, 242, 243, but take a very small step and go as an uninterrupted line process, which is now going to plus 10, yes, make a continuous line, which is basically our energy spectrum, what we wanted to see. So we will define this frequency as omega, yes, and it's going to be, well, let's start with this point, k0 minus 10 multiplied by omega base. Then we specify a step. Then we go to the last point, k omega plus 10 multiplied by omega base. So now here we have a continuous vector, yes, uninterrupted time and frequency rather in this particular case, which we can input inside of our formula and use it just like that, the same way. So BASK energy spectrum is therefore, let's call it G, going to be, well, 2 multiplied by T symbol. Don't forget that part from the formula. Yes, it's here. Then BASK of omega minus omega 0. So BASK omega minus omega 0. If we want to calculate BFSK energy spectrum, then G is going to be also double TS multiplied by 2 BASKs. BASK omega minus, wait a minute though, we have missed something that we need to also have a square here, yes, and divided by 2 tau. Let's think a little bit about this. So we kind of put 2 tau here, CBASK. So after opening brackets, it's going to be 4 tau square, CBASK square, versus 2 tau. So we can cancel one of these 2 tau and leave it with 2 tau in front, and then just to take a square. So actually, that will be simpler. Well, less to type and less clumsy code. So basically what I want to do now is to calculate absolute value of this and squared, just like this. Yes, so absolute value squared multiplied by 2 tau divided by 2 tau and 2 tau in square. Yes, so basically it was like I was writing 2 tau multiplied by 2 tau divided by 2 tau, and here we have ck squared. Yeah, so one of them cancels out and we are left with solve. Okay, then the same happens in frequency shift keying, like this component for frequency omega 1 plus the same one for frequency omega 2. And don't forget to close the brackets. So this one with omega 1, this one with omega 2, no way to replace them, no way to merge them. They are different ones, yes? So they have to be considered both. Now for BPSK, however, binary phase shift keying, it's a little bit simpler than that because here we have omega 0 and also here we have omega 0, effectively meaning that we can add them together and have here 4 instead of 2. So that is how you calculate each of these spectrums, and you only need one, whichever is for you. Although in all cases you see that we kind of depend on this BASK. Yes, well, that's how I explained it to you in lecture. We intentionally make use of Fourier transform properties and theorems to avoid having to calculate everything from zero again. So now we take a display energy spectrum with a subplot 212, and accordingly now we speak about the um, continuous process. So we use not stem but plot. X-axis shows us frequency omega. Omega is in radian seconds, so let's convert that into hertz by dividing with 2p, and then we display G. So read on, X label is going to be frequency, hertz, and Y label is going to be energy. And if we run it and do everything correctly, then we will have result, but we have some problem here. Out of memory. Okay, why that happened in the line 59? In line 59, we have calculated this. So that's the question then, what is our omega 0 or omega? Okay, so as you can see, this omega now is, well, probably it's difficult for you to see, but it's a vector of dimensions 1 with 104, 719, 755, 120. A huge array, yes? So basically here we speak about kilobytes, megabytes, gigabytes. So that's multiplied by 8, how many gigabytes it would need to have in memory to be able to just store, not maybe just store, okay, somehow it stored it, maybe it's not 8 bytes, but either way, it's a huge amount, it compresses it somehow or what. So that's because I made a small mistake here when I defined this uh, frequency range. So in fact, what I wanted to change with a step of 0.01 is this k value, not the base. So where I have specified k, here you can see like it goes from this number to this number, it's 21 value, and I just wanted to have not 21 but 2000 values, yes, to make a smooth form line. However, here what I have is not number like 140, but it's a huge number in radian seconds itself. And I go from this huge number to this huge number with a very small step. That, of course, is going to produce a lot of values. So what I'm going to do instead here is to say I'm going to factor out this omega base out, like so, so that with this step I go through k values, and then final result is going to be scaled with omega base, like so. So essentially that means I had to do omega base here also, like this, omega base here and omega base here. But I decided to simply take out this out of brackets, yes, and have it here so that it automatically will multiply with this, and with this. So now we have solved the problem, yes. We get additional error, which might be the case of trying to overfill memory. Hopefully not. Mm, but other way around, it's actually working. So let me make this line also line with 2, and graphics callback function. So this has to do something with the plot. I have some problems there. Now we have solved this task. You have two pictures. One is the spectrum of magnitude for periodical signal, and one is for random sequence. Now you need to realize that from the perspective of the spectrum requirements, actually most often this one is the good indicator, because this is considered to be how we can say the worst case scenario, the worst case scenario. So if your system and your channel and your cable or whatever else can handle this spectrum, it's easily going to handle any other combination spectrums therefore. Yes, so again, it's not if we use some kind of very specific modulation types like NRZ or EMI. In that case, this may change, but if we speak about simple modulation types like amplitude shift keying, like unipolar pulses, then actually this usually stands true. That this is the worst case scenario. And that means that you don't have to know what is the spectrum of this code sequence, or what is the spectrum of this code sequence, or of this code sequence, or whatever else, which there is billions of them of possible combinations. It suffices to know that once you calculate the spectrum for this sequence, if it's going to work and fit in your channel, then any other is probably also going to be just fine. Yes, that's why we need specifically this spectrum, which is for the worst case scenario as amplitude wise, how the magnitude is distributed in signal, and this one to get the total impression of where exactly most of the energy of your rectangular shaped signal or whatever case is focused. Yes, so you see that most of the energy is in quite narrow band, and these can be considered like leftovers, insignificant leftovers, which can be filtered or even cancelled, ignored. Yes, and you still will get a decent shape of your signal, which you can then take readings from. Yes, it's not going to be rectangular anymore, but we in telecom are not necessarily wanting to have a perfect rectangular shape, because it produces some transient processes as well. Like this process when you have, let's say, capacitor and resistor in a circuit, and your voltage was 0, then suddenly it jumps. What happens in this net circuit is the spike of current, yes, and the voltage is going to increase slowly, yes, but the current is going to spike, yes, which may damage some components as well, or your device is connected to this circuit. So that's something to consider. And we don't want that to happen in telecom equipment, yes, because of that, it's actually good for us that your data pulses will look like this one, not like two rectangular. Also, we use filter, which inevitably is going to damage this rectangular shape, so not worth to worry about in the first place. Okay, now if you change the modulation type, let's say I will now want to see frequency shift keying, BFSK, some plot, yes, everything seems to be fine. Then you see it like so, yes? That is because I have a modulation index of, let me actually change this one also. And this one as well. I comment this line, so now I want to display the frequency shift keying. This is because my modulation index is 4. That is affecting this delta omega. Now let me actually change modulation index to, let's say, 2. And we'll see how this picture changes also. Yes, so right now we have this difference between omega. We don't have anything in the center. So if I run it again, you see that now this difference is here. And something appeared in center. And also here we don't really hit to 0 like we did before. Yes, so modulation index actually says how far are these two frequencies from one another. Let me display other way around. Let's say 8. Now for 8, they are here. And you can start see them almost indistinguishably, like this is BASK1, this is BASK2. Now let me actually increase it even further to, I don't know, 16 maybe. And but this way I need to change this range maybe, but we'll see if I do. Maybe it's going to go outside of range. Well, yes, it's almost now symmetric. Now it's not symmetric here and here because of this producing some extra here, which is now adding on top of this. Yes, so that's why it's like so. Just like this one is going to produce some extra contribution here, and here that contribution is going to be smaller. So that's why it's looking not so symmetric. But for energy spectrum, you can clearly see that indeed it's combined two amplitude shift keyings very easily. Yes, and well, if we have modulation units, I believe of 0.5, then, yes, as we discussed in theory, we have almost amplitude shift keying, but the value here is not 0.25 though. Yeah, so some small changes are still there, but other way around, the spectrum really looks like an amplitude shift keying. So that's also what we discussed in our lectures. Yes. So this concludes this practical exercise, this course project task exercise. Yes. Now your course project, you can simply put those output pictures. Yes. Add some descriptions like what you calculated and how. Yes. And then accordingly, that will cover your exercise number 7. Other practical exercises in course project, we will deal the same way. Yes, once we get in our lectures to that point, we will go to this computer class and here we will do together the stuff. I will show you how to program it. I will show how to calculate it. Maybe if we need to calculate on paper, then we will show you how on paper. And then accordingly, you will be able to update it. So the idea is, as our course evolves, you will get more and more results in your course project, and when we will have last lectures, we will finish the course project with the last exercises and you will be able to submit it. Yes. But other way, it's the full semester work. Yes. You will eventually, we will have some weeks with the course project tasks, which we will accordingly gradually go through the full list of all these tasks. Yes. So I already said that task 1 can be done already because that was our very first lecture, this diagram we discussed. Then once we get about information theory, we'll start working on this. After that, we'll switch to the error correction codes to do this stuff. Then we will discuss optimum receivers, how exactly to receive in noise to do this part, and finally with the coding this part, which is going to be the most difficult part of exercise, but also that's the only way to get a really good grade, yes, to do all of these tasks, which is, I believe, fair, considering that I shouldn't ask too much to get a low grade, but if you want to have a good grade, then you have to show your knowledge and skills. So in that sense, I believe it's balanced. Okay, thank you then for attention. And then, as again, I wanted to mention so this Thursday we do not meet, we do not have any class. I will send a message in notice to everybody because I need to participate in some other activity which happens at the same time. So basically, that means we will meet next time on Monday. And we will also have a practical exercise, not a course project, just practical exercise related to channel models. Thank you for attention.